Welcome class. Today, we are going to proceed with part of Chapter 1, which is on capacitor. These are the learning outcomes of this subtopic. The first one is, we will see the reason behind why we group capacitors as the energy storage elements. Second, we are going to see the relations between current and voltage across capacitor. The final learning outcome is, you will be able to calculate the total equivalent capacitance, when the capacitors are arranged in series, parallel or the combinations of these. So, what is a capacitor? Capacitor is the structure comprises of two conductive plates being sandwiched with a dielectric material. The dielectric material has an insulator property that would prevent the movement of charges between the two conductive plates. There are many types of capacitors available in the market. For example, here we have an electrolytic capacitor, which has polarity that we need to be careful in making the circuit connection. There is also the ceramic capacitor and the surface-mounted technology capacitor for the flat printed circuitry. Although the structure seems very simple, in actual design, it does not. Over here, we have three different designs for the capacitors mentioned before this. For the electrolytic capacitor, it is made by rolling the conductive plates that have been separated by a dielectric material to form a cylinder. Whereas for the ceramic capacitor, the dielectric material is made up of ceramic that has been placed in between the electrodes. Then, the whole thing is coated by a hardened material to form a whole package as shown in the figure here. Similarly, in the case of SMT capacitor. However, the structure is formed by interleaving the dielectric materials with the internal electrodes. When we connect a capacitor to a battery, the electrons on the top conductive plate are attracted to the positive terminal of the battery and move towards it. This makes the top conductive plate to be positive compared to the bottom one. The movement of electrons stop when the potential across capacitor is equivalent to that of battery. And the charges are kept inside the capacitors. This is how the energy is being stored in the capacitor. Although the electrons are attracted towards the positive terminal, they would not be able to jump to the positive terminal because there is an insulation provided by the dielectric material. The amount of charge stored in the capacitor Q is equals to C, that is the capacitance, multiplies with V, voltage. In other words, we can say that capacitance is the ratio of charges on one plate to the potential difference between the two conductive plates. Capacitance is dependent on the structure it is made from. For a parallel plate capacitor, its capacitance is equivalent to the ratio of product of permittivity of dielectric material and surface area to the distance between the plates. Therefore, it also dependent on the materials that we used to make the capacitor because epsilon differs from one material to another. Now, we are going to see the connection between current and voltage across a capacitor. We start with the amount of charge stored in the capacitor, Q equals C times V. Differentiate this with respect to time. We use the definition of current, which is I equals to the rate of charges. Hence, we get the expression of current across capacitor as I equals C times the derivative of voltage. If we have a plot of I against the dV over dt, the capacitance is obtained from its slope. From this expression too, the voltage across the capacitor must not be an instantaneous change. Conversely, we treat the capacitor as open circuit when it is operating under direct current. To find the voltage expression, we integrate the current expression with respect to time and rearrange it. Please note that the voltage depends on the charges being stored in the capacitor. What about the power and energy stored, or work done by a capacitor? Using the general equation of power, which is a multiplication of current and voltage, The power delivered to a capacitor P is given by the capacitance C times the derivative of voltage V. Meanwhile, for the energy stored, W, from its definition, we get W equals to capacitance C times the integration of voltage. Integrating the derivative of voltage from time equals infinity to time equals t, we obtained the energy stored in a capacitor W equals to half of capacitance times the V square. Although it is equivalent to half of the energy supplied by a source, there is no energy loss by a capacitor. Energy is lost by the source, instead. Remember that, there is no energy loss by a capacitor. This is the main characteristic of an ideal capacitor, which will be applicable throughout this subject, unless otherwise stated. Now, we are going to see the equivalent capacitors when they are arranged in series. Let's say we have 3 capacitors in series. To obtain the voltage expression, we apply the Kirchhoff voltage law KVL. After substituting the general expression of voltage across a capacitor and group them accordingly, we can see that the total capacitance is similar to that of total resistance in parallel. Well, what about the equivalent capacitors when they are arranged in parallel? Over here, we have 3 capacitors line up in parallel. To obtain the current expression, we apply the Kirchhoff current law KCL. Then, we use the general expression of current across a capacitor and sort them accordingly. Once we do that, we can see that the total capacitance is similar to that of total resistance in series. Finally, we are going to see the way to calculate the total capacitance when several capacitors are connected, in a combination of series and parallel, as shown in this diagram. We utilize the 2 properties that we have in previous cases, that is, we treat parallel capacitors in the same manner as the resistors in series, and that of series capacitors similar to the resistors in parallel. The equivalent capacitance for this circuit is.
This the end of part 1 of chapter 1. In the next part, we will learn another energy storage element, that is on inductor. Thank you.